Hi, my name is Mr. Rodriguez, and this video is going to cover all of the things that I feel like we need to know as prerequisites to start studying physics, at least algebra-based physics. And the first thing that I want to mention to you is vectors. So let's take a second to discuss what vectors are, because you definitely need to know what they are in order to start studying physics. So first off, by definition, a vector is a quantity that involves both magnitude and direction. Okay, so if you don't know what magnitude means, it's really just the size of something. So what I mean is, a vector is something that has size and has direction. So think of it like this. When you apply force to something, like you're moving something or you're pushing against a wall, right? That force has some size. It's either a weak force or a strong force, but it also has some direction. You can't apply force and not apply force in some specific direction. So what that means is, anytime that you're discussing how much force you applied to something, you can always discuss both how strong that force was and in what direction that force was applied. So what that means is, I want you to start thinking about vector quantities as arrows, all right? If you just think of vector quantities as arrows, that can get you through a lot of physics. That said, there's also something called a scalar. Now, a scalar is something that you can't think of as an arrow. Think about how much mass something has, like the mass of a pumpkin, all right? The mass of a pumpkin doesn't have a direction. It just has an amount, okay? You don't think about what direction the mass of a pumpkin is, all right? So this kind of a quantity, we call it a scalar, a quantity that has no reference to direction. So it's something that just has size. So there's always just two kinds of quantities in physics, a vector quantity or a scalar quantity, all right? And a vector quantity you could think of as an arrow, and a scalar quantity you cannot, all right? So that said, when you're discussing vector quantities, there are several ways you can denote them, all right? On print, usually they will be bolded or italicized, but sometimes they will have an arrow over them, all right? And the most common handwritten notation is typically just writing the name of the vector normally, but with an arrow on top of it. All right. So the first thing you need to really know about vectors mathematically is the fact that they follow the commutative law of addition. Now, of course, in physics, when we start to study physics, there are certain things about mathematics that we're going to have to assume that you have learned. The commutative law for addition is the first one. All it means, and it's pretty simple, is that A plus B is equal to B plus A. So when you move around letters when you're taking their sum, it doesn't actually affect anything. Vectors follow this law. And what I mean is, if you take some vector A and add vector B to it, that's the same thing as taking some vector B and adding vector A to it, right? And if you look at this image here on the right-hand side of the screen, you'll see, like, if we start with A, okay, we start with A, and then we add B to the tip of A, all right, then we're going to get some vector A plus B that you see here. But if we started with B down here, and then we added vector A to the tip of that, then we're going to get some different vector B plus A. And if we take A plus B and B plus A and we put them right next to each other, you'll notice that they're not only are the exact same length, but they're also pointing in the exact same direction. So what that means is that A plus B and B plus A are essentially equal to each other, all right? Proving that that vectors do follow the commutative law for addition. All right, so what did we just do here? What we did was we were graphically adding together two vectors. And so how do we do that? I mean, it's pretty simple. So let's say that we have some vector A that's not being added to vector B right now. So this orange vector is vector A. And then we have this vector B here in purple, and we want to add them together, right? So the order does kind of matter, but the result is going to be the same. If we're starting with vector A, okay, we start with vector A, then we're going to place it somewhere such that we can place vector B at the tip of it. So we're going to touch the tail of vector B to the front tip of vector A, and the resultant vector is actually going to be you connecting the tail of vector A to the tip of vector B. So you're basically making a triangle here. And the resultant vector, the sum vector, is right there. And you'll see it here. I've already done it here to the right. That vector is now vector A plus B. And so my green vector on the left should be equal to the gray vector on the right. A plus B, it's the same thing. So that's why I said at the beginning of the video that you should really try to think of vectors as arrows, right? Because the arrow is going to point in the direction that the vectors is pointing, and you can give it some length that's equal to the value of the vector. So let's say that you wanted an arrow to represent 10 newtons of force, then, well, you could just draw an arrow that's 10 newtons long, so that represents how much force, all right? Or let's say we're not using newtons, we're using distance, so you could draw an arrow that's like 10 centimeters long and say that each centimeter counts as 1 newton, all right? And then you point the arrow in the direction of the force. So that way that arrow, that 10 centimeter force represents your 10, that 10 centimeter arrow represents your 10 Newton force. Now that we've discussed how to add vectors graphically and thinking about them as arrows, the next thing I need us to know before we start studying physics is the concept of a scalar multiple. So a scalar multiple, as I've kind of already introduced to you the fact that there's vector quantities and scalar quantities, a scalar multiple is when you multiply a scalar quantity by a vector quantity. Okay, so by definition, the operation of multiplying the magnitude quantity of a vector by a scalar quantity. The result is a vector, and that vector generally is going to have the same direction as the vector in the scalar multiple. All right, let me show you exactly what I mean here. Let's say we start with some vector A, okay? We start with some vector A, and we want to multiply it by some scalar 2. Well, 2 is just a scalar. It doesn't have direction, so when I multiply it by vector A, then I'm not going to affect the direction of vector A. All I'm going to do is I'm going to affect the size of vector A. And if I'm multiplying A by a scalar 2, then I'm going to change that size by a multiple of 2, meaning that my new vector is just going to be twice as long as my original vector, but it's going to be in the same direction. There are a lot of physics principles that are built on the concept of a scalar multiple. So yes, if we started with a vector A and we multiplied it by a scalar that is equal to 1/2, then you're just cutting the length of your vector in half, but the direction is the same. Now, there is an exception to this rule. If you multiply by a negative scalar, look here in green, we actually just have a negative sign here. That's the same thing as multiplying by -1. This is the only instance in which you will change the direction of the vector, all right? If your scalar is negative, then what that's going to do is it's going to flip the direction of your vector. You will have the opposite direction, okay? And that's very useful for the next topic we're going to cover, which is vector subtraction. But generally in physics, when you're taking scalar multiples, you're taking the measurements of things, and measurements are not usually negative. So that's why we say generally scalar multiple results in a vector of the same direction. But of course, mathematically, you can break that. You can say, well, I want to multiply by a negative scalar, in which case the result will be a vector that's still pointing along the same line, but in the opposite direction. All right. So now that we have discussed the concept of a scalar multiple, I want to talk about vector subtraction, or at least graphical vector subtraction, because we discussed vector addition, and I wanted to tell you that vector subtraction is the same thing as vector addition, but we throw in a negative scalar multiple in there. And so what I mean is, if you wanted to take vector A minus vector B, it's better to multiply vector B by a scalar -1, flipping its direction, and adding it to vector A. And so you should know mathematically that this is the same thing, right? A minus B is equal to A plus -B. But if we want to actually add things graphically, it makes a little bit more sense to take into account the fact that we are using a scalar multiple here, right? I don't want to do A minus B. I want to do A plus -B. And in order to get -B, I have to multiply B by -1. And so as long as I understand how scalar multiples work, I understand that that's all that's going to do is that's going to take my original B and it's going to flip its direction. We're still going to have the same length, but it's going to flip its direction. And now instead of taking the difference, I can just take the sum. All right. And then so that's going to follow the exact same process as vector addition. The resultant vector is going to be the same thing as a vector A minus vector B. We can also write it as vector A plus negative vector B. So I want you to take a moment to fully take in how the concept of scalar multiple is used for this process. Now let's get into the concept of two-dimensional vectors. We were already using two-dimensional vectors. We were kind of discussing them like dimensions didn't matter. All right, because when we're talking about two-dimensional vectors, we're talking about vectors that have a vertical component and a horizontal component. So what I mean here is, like, look at vector B and vector C. B is horizontal and C is vertical. So they're both considered one-dimensional vectors, okay? But B plus C, it has some vertical component and it has some horizontal component. So we would call it a two-dimensional vector, okay? Meaning that its vertical position changes and its horizontal position is changing. And you can tell that for sure because it's made up of both B and C, all right? So two-dimensional vectors lie flat in a plane and can be written as the sum of a horizontal vector and a vertical vector. They always can, all right? So you've already seen this, but of course, here are two more examples. B plus C is a two-dimensional vector made up of B and C, and E plus F is another two-dimensional vector made up of vectors E and F, all right? So, of course, B plus C is a two-dimensional vector, but so is E and F, and we can actually add these two together, all right? We can actually add two two-dimensional vectors together to get another two-dimensional vector, all right? So this vector, this pink vector here that we get as a result of adding E and F to B and C, or adding E and F to B and C, it's also a two-dimensional vector, but it's not as straightforward to write in terms of vertical and horizontal parts. All right, that's why we use something called unit vectors. So a unit vector is a vector with a magnitude of 1. All right, so we use unit vectors as a standard for representing the most common directions in geometric space, basically up and down or left and right. All right, at least when we're talking about two dimension. All right, so this helps keep notation simple and consistent for scientists all over the world. In one-dimensional geometry, the only unit vector we deal with is I hat, okay? And I say I hat because that little symbol above is generally referred to as I hat, at least in my part of the world, all right? So, or it's referred to as a hat, even though it's a caret symbol, you know. Now, this I hat has a default direction of to the right, okay? But if we're talking about just one-dimensional motion, it could be up or down, okay? If you're just using one dimension, whether it's horizontal or vertical, then you just use I hat. So it could mean up or it could mean to the right, depending on how you're setting your frame of reference. All right. Now, so if we're working on some vertical number line like this, then I hat would look like this vector. Remember, it is a vector, so it can be represented as an arrow. It just has to only be 1 unit long. All right. So let's say I wanted to define some vector as the name 3I hat. Okay. So that's a scalar multiple. It's my unit vector I hat times the scalar 3. And it represents a vector that is in the same direction as I hat, but is 3 units long. So hopefully you can see how that's a useful way of naming things by the scalar multiple of some scalar and a unit vector. So you automatically know what direction it's pointing. All right. So understand that multiplying a number by a unit vector results in a vector always. So multiplying a unit vector by a scalar just gives you another vector. So of course, with two-dimensional vectors, we have to have two different unit vectors. I represents the direction on the positive and negative x-axis, and J is going to typically be the letter we use to represent positive or negative on the y-axis, okay? So when working with two-dimensional vectors, we always use I as the horizontal unit and J as the vertical unit vector. So the two-dimensional vector A that you see here on the screen has the horizontal component 2I hat and the vertical component 4J hat. All right, so we can say that we can actually define the vector A as the vector sum of the vector 2I hat and the vector 4J hat. All right, and it's very common to name a vector by a vector sum and those vectors in the vector sum to be scalar multiples of unit vectors, right? Because it tells you all the information you need. It tells you the direction, it tells you the length of the components, and it really tells you how to draw it on a two-dimensional grid, right? Your horizontal leg has to be 2 units long, and your vertical leg has to be 4 units long, and then you just make a triangle, and the hypotenuse is your vector. That's why that's so useful. You can take the 2I hat plus 4J hat, draw it up on a grid, and then you have your vector. Now, it also helps mathematically because we can add things together really easily. So if we had some second two-dimensional vector, say vector B, such that B was defined as the vector sum of 5I hat plus 3J hat, then A plus B would literally just be the 2I hat plus the 5I hat, 2 plus 5I hat. and then plus the 4j hat plus the 3j hat, 4 plus 3j hat. Likewise, b minus a is even easier than when we're doing it graphically, because we can just take 5 minus 2 I hat, 5 minus 2 I hat, plus 3 minus 4, 3 minus 4 j hat. Here, let's sketch the vector a plus b. All right, so based off of the a plus b, a and b that I had here, I've drawn a here for you and b here for you. And as we saw before, 2 plus 5, that would be 7, all right? And then 4 plus 3 would also be 7, so we'll have some vector that's 7 I hat and 7 j hat after we add them together. So graphically it all works, and algebraically it all fits together very nicely. So what happens if you're given some vector and it's defined by its vector sum using scalar multiples of unit vectors, but you have to find its length? Because it's really easy to know the length of a one-dimensional vector, but it's not super immediately straightforward to find out what the length of a two-dimensional vector is. So like, how long is this purple line? I mean, I know that it has a 6-unit horizontal component and a 7-unit vertical component, but that doesn't mean that 6 plus 7 is how long this line is. No, you'll notice that this is a right triangle. So the length of our actual vector here is actually the hypotenuse of this right triangle. So yeah, so then you'll find it in the same way that you'd find the hypotenuse using Pythagorean theorem. So then we could say that the magnitude of this vector 6 I hat plus 7 j hat is actually just the square root of 6 squared plus 7 squared, all right? So we call this the magnitude because the value of a two-dimensional vector's length does not apply any direction, all right? So if we're just talking about the length of this arrow, it would be the same length whether it was pointing this way or if it was pointing this way or even this way. So here I say sketch the two-dimensional vector with components 6 I hat plus 8 j hat, all right? And here, let me erase this so you can see how I would do it just from scratch. All right. If I wanted to sketch a vector that was 6 I hat plus 8 j hat, then I would just look at the 6 I hat. I know that's on the x-axis. Okay, so I'd be 1, 2, 3, 4, 5, 6. All right. I know my vector has to come to here, and then 1, 2, 3, 4, 5, 6, 7, 8. Great, so this is 8 and this is 6, and I know my vector needs to go to both of these points. So I'm going to kind of try to find where they meet up on the grid. All right, it'd be easier if this was on grid paper. And then from there, I'm just going to go ahead and draw a straight line from the origin. All right, that's my vector, okay? And if I wanted to actually show the vertical component, I could right here. If I wanted to show the horizontal component here, of course, we have my right triangle. All right, this vertical component is, of course, my 8 j hat vector. All right, and this horizontal component is, of course, my 6 I hat vector. All right, and then if I wanted to find how long this was, it would just be a matter of taking the square root of 6 squared plus 8 squared. All right, 6 squared plus 8 squared is, of course, 36 plus 64. Yeah, that's 100. So root 100 is 10. The magnitude would be 10 units long. Now, finding the direction of a vector can be a little bit more tricky because you have to bring in a little bit of right triangle trigonometry. Now, I do have a note here, review right triangle trigonometry before moving forward because I'm going to be talking about it relatively quickly. The direction of a vector is, especially on a two-dimensional grid, specified as the angle that your vector makes, okay, the angle that your vector makes with respect to the positive x-axis. So we're always going to start at the positive x-axis and we're going to make an angle. We're going to make like this little angle until we touch our vector. So that means that here, this angle theta, is our direction, and that's how we have defined the direction of the vector. All right, so we call this angle theta. We use the vector's components and any inverse trig function that we need. Usually we just stick to tan inverse to find angle theta. So you might want to recall SOHCAHTOA. That's pretty useful for this. I don't know how comfortable you might be with the right triangles trigonometry, but you should review it if you're doing physics. That said, tangent, this part right here, tangent is defined, right, as the opposite. Tangent of any angle theta is defined as, in a right triangle, the opposite leg, okay, the opposite leg over the adjacent leg. All right, and when I say the opposite leg is, I mean, if we're talking about this angle, the opposite leg would just be this leg, and that's 7. And that would be 7 over your adjacent leg. And if we're talking about this angle, the adjacent leg is the one that's touching it. That's 5. All right. So then tan theta would be equal to 7 over 5. But we don't know what theta is, so that's why we use the inverse tan function. So by definition of the inverse tan function, we'd say that tan inverse is tan inverse of that opposite over adjacent. So tan inverse of 7 over 5 is equal to our angle theta. All right. And so we'd want to plug tan inverse 7 over 5 into the calculator to find angle theta. And if you did that yourself, making sure that you kept everything in degrees, you'd get something about 55 degrees for this angle. And if you look at this kind of does look like it's about 55 degrees. So that's how you would find the direction of a vector if you had the name of the vector based off of its components. Yeah, so that's pretty much it for this first set of notes. All right, this is pretty much everything you need to know to start talking about physics. Yeah, there is a lot more mathematics in Physics 1, but this is the very crucial bit of mathematics that you need to start talking about the first unit in physics, which is kinematics, or how objects move. All right, can't wait to talk to you in the next lecture. We're going to start talking about kinematics, specifically displacement, velocity, and acceleration.